This demonstration is about amplitude modulation. Now we can define amplitude modulation as a modulation technique where the amplitude of the carrier is varied in proportion to the message signal or the information bearing signal. Now in our demonstration we are going to use a simple sine wave as an information bearing signal, as my message signal. In practice this need not be true. We can have a message signal which is more complicated. It can have a certain bandwidth. For example, if you are sending voice information by amplitude modulation, we know that voice signal occupies a bandwidth from 300 Hz to 3.4 kHz. So it has a certain bandwidth. But if you see the actual waveform, it may be a complicated waveform. For demonstration purpose, for our understanding, we will use a simple sine wave as the modulating signal or the information bearing signal, and we will use the high frequency carrier to send this information. So let me, before I start the demonstration, I will just describe to you the kit that we use for demonstrating for this demonstration. This is the kit we are going to use. In this kit, there is a portion which generates a low frequency signal or the modulating signal. There is a high frequency carrier circuit which can generate carriers up to 1 MHz and beyond that. This is a low frequency signal which can generate signals up to 1 kHz maximum, and this can up to 1.5 kHz it can generate the carrier frequency. So sorry, 1500 kHz it can generate carrier frequency from 500 Hz to 1500 kHz. Now for our demonstration we are going to use, we will first measure the carrier frequency and the message signal frequency individually on the oscilloscope and then give it to the modulator. To carry out amplitude modulation, I require a carrier signal, a message signal and a modulator. So I will feed in the carrier signal and the message signal into the modulator. At the output of the modulator I should get amplitude modulated signal. Let us measure the individual signals individually on the oscilloscope, and then we will give it to the modulator and see how the output looks like. Now first let us measure the information bearing signal or the message signal. So if you see the oscilloscope, at the bottom you see it is mentioned the frequency is being measured. Now this is a sine wave. Frequency is about 2 kHz. Okay, so this is the information bearing signal for us. This is a 2 kHz frequency. Next let us measure the carrier frequency. The carrier frequency is measured as about 503 kHz. I will just adjust it to about 500 kHz. Yeah, it's about 500 kHz carrier frequency. So you can note down, message signal frequency is 2 kHz, the carrier frequency is 500 kHz. So now we are going to feed in these two signals into what is called as a product modulator. In this kit, this is product modulator. This is called as a balanced modulator. It has got two inputs. One is for the carrier, the other is for the signal. So I will feed in the carrier from here. I will feed into this carrier input. I am taking message signal from here, from this one. I am connecting it to the signal. So this is carrier is 500 kHz. Message signal is 2 kHz. At the output I am going to generate an amplitude modulated signal. So let us connect the output to the oscilloscope and see how the AM signal looks like. So what you are seeing on the screen is a typical amplitude modulated signal. Let me just change the time base. So what you see here is the high frequency carrier, and the amplitude of the carrier is being modulated by the message signal. So the envelope what you see here is the low frequency message signal that I have, which was 2 kHz frequency, and the amplitude of the carrier is being modulated by this low frequency message signal. So this is basically how an amplitude modulated signal will look like. If you see your textbook, you will see a similar diagram given in the textbook, which is showing the amplitude modulated signal. Now the equation of amplitude modulation is shown here. Now this is a modulated signal phi am of t, which is equal to a plus mt cos omega ct. Omega c is the carrier frequency in radians per second. This capital A is the carrier amplitude. This m of t is the message signal, which is given by mt cos omega mt. Omega m is the message signal frequency, again in angular frequency. mp is the peak message signal amplitude. So this is mp is the message signal amplitude. So this is my message signal, and this is how the amplitude modulated signal looks like. If you forget about this A, this mt multiplied by cos omega ct is what we call as the double sideband suppressed carrier. To this, if I add a carrier that is A cos omega ct, then this becomes amplitude modulation with transmitted carrier. We call it as AMTC, amplitude modulation with transmitted carrier. So this is the equation for an AM signal. Now we define a quantity mu, which we call as modulation index, which is equal to the ratio of the message signal amplitude to the carrier amplitude. So we can vary the modulation index from, let's say, 0 to maximum 1. We would not like to have mu greater than 1. We'll tell you why. If the message signal amplitude becomes equal to the carrier amplitude, mu is equal to 1. If message signal amplitude is half of the carrier amplitude, then mu is half. I can vary the value of mu by changing the message signal amplitude and the carrier amplitude, the ratio of this. In terms of mu, I can write the same equation which is given here. I can write this as phi amt equal to capital A times, in brackets, 1 plus mu cos omega mt bracket closed cos omega ct. So this is another way of writing the same equation, where I have written, in place of mt, I have written this expression, and I have multiplied and divided the expression by A to write it in terms of mu. So this is another form of amplitude modulation equation, the same equation written in terms of mu. Okay. So now let us see experimentally what is the value of, how do I modulate, under modulate the signal, over modulate the signal, and have 100% modulation. If mu is 0.5, I call it as 50% modulation. If mu is 0.8, I call it as 80% modulation. If mu is 1, I call it as 100% modulation. Okay. Now, how do I change the value of mu? If I change the message signal amplitude, I'll change the value of mu. Let us try to change the value of mu. If you notice, this is less than 100% modulation. This is also an AM signal, but with a modulation index less than 100%. Okay. Let me show you more than 100% modulation. This is more than 100% modulation. Notice this point, what happens, okay? And just concentrate on this point when I make it less than 100% modulation. This is less than 100% modulation, okay? So this top envelope and the bottom envelope just almost are about to touch. At 100% modulation, what happens? This is almost 100% modulation. Okay? Look at this point. Now this is more than 100% modulation. Look at this small portion that is developing in between the two big lobes. Okay, so this tells you that this modulation scheme is having a mu value greater than 1. So this is more than 100% modulation. Now, when we want to demodulate the signal, what are we interested in? Inside this envelope is the carrier frequency. We are not interested in the carrier frequency. What we are interested in is in recovering back this message signal waveform. That is, I am interested in recovering back this low frequency waveform. If I set mu greater than 1, what will happen? When I am trying to detect it, I am not going to get exactly the same waveform as it was at the side of at the transmitting side. There is a slight distortion here. The envelope detector is going to trace the envelope, but it's not going to generate the actual waveform. There is a slight distortion here because mu is greater than 1. So we do not want a situation where mu is greater than 1, because mu greater than 1 would lead to distortion. I will not be able to recover back the original signal that I transmitted. So we always keep mu less than or equal to 1, so that I can recover back the original signal. Now this is how the time domain picture looks like. The time domain waveform looks like amplitude modulation. Now, as I said, as a communication engineer, we are always interested in the frequency domain representation of the same signal. So we will now connect this signal to the spectrum analyzer and see how the AM spectrum looks like. Now remember, before we go to the spectrum, we measured the carrier frequency to be 500 kHz. We measured the message signal frequency to be 2 kHz. So if you go back to your textbook and notice, you will see that the upper sideband and lower sideband are located at 502 kHz and 498 kHz. That is FC plus FM and at FC minus FM. FC is 500 kHz, FM is 2 kHz. So I will have FC plus FM 502 kHz and FC minus FM 498 kHz. So that's where I should expect. So you should have a rough idea where should your modulated signal lie, so that you can appropriately set your spectrum analyzer to measure the spectrum. So now I am going to move the marker. So that marker here, the marker is now placed at this point. Now this central peak which you see, that shows the carrier frequency. Okay, so you see the marker 500 kHz. This is the upper sideband and this is the lower sideband. As I said, upper sideband should lie at 502, we have calculated that. The lower sideband should lie at 498 kHz. Let's try to measure that. We will move the marker to the right side. (502 kHz), upper sideband at 502 kHz. This is what we had calculated. Now let's find out where the lower sideband should lie. So it's at 498 kHz. Now what do you notice from this experiment? The message signal frequency was 2 kHz, but the modulated signal frequency has a bandwidth of 4 kHz. That is 498 kHz to 502 kHz. What does this tell us? It tells us that if the modulating signal has a bandwidth of 2 kHz, if the modulating signal has a bandwidth of 2 kHz, the modulated signal will have a bandwidth of 4 kHz. Amplitude modulation will occupy 2W bandwidth if W is the bandwidth of the modulating signal. So the AM signal will require twice the bandwidth of the modulating signal for it to be transmitted over a channel. Okay? So this is amplitude modulation with transmitted carrier. The carrier is also present. Very often we don't require the carrier to be transmitted, because carrier by itself doesn't convey any information. On the other hand, it takes away a significant portion of the transmitted power. So it's not an efficient scheme. We can also generate amplitude modulation by suppressing the carrier. Okay? So we transmit both the sidebands, but with the carrier suppressed. The carrier power is much less here, and so we call this scheme as double sideband suppressed carrier. So how do I make a suppressed carrier here? I need to bring down the carrier power. There is a facility in this kit by which I can reduce the carrier power. Now notice, just watch the stream and concentrate on the central peak. Notice what is going on. The carrier power is going on reducing, and at a certain position the carrier power is much smaller than the power at both the sidebands. So this is a situation where I have double sideband suppressed carrier. The peak positions are still 490 kHz and 502 kHz, but then I don't have a carrier component as such. So in this situation it is simply MT multiplied by cos omega Ct. So we call this kind of waveform as double sideband suppressed carrier. Now you may have a question as to if the carrier is not being transmitted, how do I demodulate the signal? The point to be noted here is, in a double sideband suppressed carrier transmission, we do transmit carrier but at a much lower power. We call this as a pilot carrier. Now this pilot carrier is used by the demodulator to demodulate and recover back whatever information has been transmitted. Okay, so this is how a double sideband suppressed carrier spectrum looks like. Now DSP-SC signal also occupies a bandwidth of 2W. So both AM as well as DSP-SC occupy the same bandwidth 2W, where W is the bandwidth of the modulating signal. But the advantage of DSP-SC is it is more power efficient than AMTC, than the situation where you are transmitting the carrier also. Okay, so this is how amplitude modulation is being done. So I gave the input to the product modulator. The input consisted of the carrier frequency and the modulating signal. Okay, the carrier signal and the modulating signal. And at the output of the modulator, I had the AM signal. Now, if you were to transmit this on a wireline channel, the output will be the channel here will be, let's say, a twisted pair of copper cables. So then I have the output of the modulator straight away feeding into the copper cable. If it's a wireless transmission, then I have to have an antenna and a matching circuit before that, so that I can radiate this information over the antenna, and then this can propagate in the free space. This is what is done in your radio stations, typically the AM stations, where there are huge antennas which radiates information in free space, and you can tune your receiver. Your radio is basically an AM receiver which tunes to a particular carrier frequency and receives information, and that's how you are able to enjoy the music or audio programs. So far we talked about amplitude modulation. Now let us look at demodulation. Now in class we have learned that amplitude modulated signal can be demodulated in two ways. One is I can do an envelope detection. Second is I can do a coherent detection. Envelope detection is very simple. It's very inexpensive to build, a small circuit, but coherent detection requires a little bit of care. Now when you're talking about AMTC, that is when I'm transmitting a carrier also along with the modulated signal, then it is possible if I use another carrier at the receiving end, and if these two carriers, the one which is transmitted and the one which is at the receiving end, if these two carriers are in phase, then it is possible for me to demodulate information. We have seen this in the class. There is a simple mathematics that you can work out to find out how to get the MT, the value of the message signal, how to recover it back at the receiver. Now envelope detector is very simple to build. It just tracks the envelope of the modulated signal and from there demodulates the information or receives information. Now in this kit we do not have an envelope detector, but we have a synchronous detection facility, but there are some problems with the kit. Perhaps the components inside the circuit are not ideal, so there is a distortion in the output signal, but we will try to show you the concept. Now in this kit, I showed you when we talked about modulation that this was the carrier frequency circuit, the circuit that generates the carrier signal. When I am doing a synchronous demodulation, now this is another balance modulator. Okay, so let us, this is another balance modulator. To the input of this modulator, I'll give the modulated signal, and the other input of this modulator, I'll give the carrier signal. This is a locally generated carrier signal, and this is the modulated signal. So the demodulated signal will be available on low pass filtering. So if you have modulated signal, you're multiplying this modulated signal with another cos omega Ct term. So you have a cos square omega Ct term, which you can write in terms of 1 plus cos 2 omega Ct. Okay. So 2 omega is a higher frequency component. I am trying to filter that out using a low pass filter, giving me only the message signal. So at the output of this I must have message signal available, but ideally speaking you should be able to recover back the message signal, but in this circuit there is some problem with the circuitry inside, and these are the practical problems you will face. Now this is where you need to sharpen your skills at circuit building, and you know conceptually that you should be able to recover back the message signal. So you should try to recover back your message signal, play around with the circuit parameters and get the optimum result. That is, the message signal should be able to be recovered without any distortion. This is what your radio receivers do. The amplitude modulated signal, when you receive an AM station, you are basically tuning your radio receiver to receive the carrier frequency at that particular station and then receive the information whatever is being broadcast at that station. So this is how your radio receivers work. And there will be some amount of noise that is added onto the AM signal, which is one of the disadvantages of AM transmission. But nevertheless, when we tune it properly, we always get a fairly good signal level. Okay. This demonstration is about frequency modulation. The previous demonstration was on amplitude modulation, where you saw that the amplitude of the carrier was varied in proportion to the message signal. In frequency modulation, we vary the frequency of the carrier in proportion to the message signal. So you must understand the definitions, the two definitions very clearly. In amplitude modulation, we vary the amplitude of the carrier in proportion to the message signal. In frequency modulation, we vary the frequency of the carrier in proportion to the message signal. Now we again have a kit with which we can demonstrate the concepts of frequency modulation. Now during this demonstration you will see how an FM signal looks like in time domain, how the spectrum of an FM signal looks like, what is narrowband FM, what is wideband FM. These concepts have been covered or will be covered in the class lectures. Now this is a kit which is generating the frequency modulated signal. Now in this kit, you will be aware when we talked about amplitude modulation, we talked about the carrier signal. Now this circuit is a voltage controlled oscillator. That is, the oscillator's frequency changes depending on the input voltage. The input voltage or the message bearing signal in this case is a simple sinusoid, a sinusoidal signal that I have taken from the function generator. The sine wave is set at 20 kilohertz. So frequency of the sine wave is 20 kilohertz. Now this sine wave, which is the modulating signal, will be input into this VCO. The VCO will produce a frequency modulated output. Now the frequency of the carrier is varied in proportion to the message signal. That is, the oscillator frequency changes in proportion to the message signal. So in effect, you are generating frequency modulated signal. We will just demonstrate the concept. Now before that, as usual, let us measure the message signal frequency separately and the carrier frequency separately and satisfy ourselves that these are the frequencies we are feeding. Now here, you see the oscilloscope. This shows a frequency of 503 kilohertz or so. Let me adjust it slightly. So that's about 500 kilohertz. When you don't connect any input to the voltage control oscillator, the voltage control oscillator will oscillate at its natural frequency, which is called as the free running frequency, and that free running frequency is 500 kilohertz. That is the frequency of the carrier we have chosen. Now FM, unlike amplitude modulation, is little more involved. The analysis of FM is quite difficult compared to the amplitude modulation. But for demonstration purpose, it becomes simplified if we choose the message signal to be a simple sinusoidal signal. Now, I have the sinusoidal signal coming from here, the message signal coming from here, and let us measure the message signal signal. So, the carrier frequency is 500 kilohertz. Let us measure the message signal frequency. So this is the message signal I have, the sinusoidal signal, and the oscilloscope measures the frequency to be about, let's say, 20 kilohertz. So the message bearing signal, the sinusoidal signal, has a frequency of 20 kilohertz. The carrier has a frequency of 500 kilohertz. Now what we'll do is, we'll give this message signal that is coming from this function generator to the input of the VCO. At the output of the VCO, I would expect a frequency modulated signal. Now, what you are seeing on the screen is the typical waveform, time domain waveform of a frequency modulated signal. Notice that, let me expand the time scale. Notice the way the frequency is changing. This is the frequency of the carrier that is changing. Now, if you go to the FM equation, this is the equation for frequency modulated wave. Phi FMT is the frequency modulated signal, which can be given by A times, A is the carrier amplitude, multiplied by cos omega CT plus KF. KF is called as the frequency constant of the modulator, times integral of m lambda d lambda. M lambda here is mt, which is equal to np cos omega mt. Omega m is the message signal frequency, the angular frequency. So mt equal to np cos omega mt. So I integrate the message signal, phase it and feed it to a phase modulator. What I get is frequency modulated signal. Okay. If I do not integrate this would simply become a phase modulated signal. If I integrate this becomes a frequency modulated signal. I integrate this, pass it to a phase modulator, the resultant is a frequency modulated signal. Now this Fi is called as the instantaneous frequency because the frequency of the carrier is changing in proportion to the message signal. So we talk about an instantaneous frequency which is given by Fi, which is equal to Fc plus Kf by 2 pi times Mt. Mt is your message signal, Nt equal to Np cos omega Mt. Now we define a quantity called as beta, which we call as modulation index. If you see in the case of amplitude modulation, we defined a quantity called mu, which was a modulation index. In this case, this is beta is called as the modulation index, which is given by delta f divided by b. Delta f is the frequency deviation. It is called as the frequency deviation, which is given by kf by 2 pi times np. What is np? Np is the amplitude of the message signal. So delta f is the frequency deviation divided by b. B is the bandwidth of the modulating signal. So delta f divided by b is given by beta, which is the modulation index. So it is the value of this beta which tells us whether this frequency modulated signal is a narrowband FM or a wideband FM. For small values of beta, this is approximately a narrowband FM. For large values of beta, it becomes a wideband FM. Now, by looking at a time domain representation of FM signal, you will not be able to make out whether it's a wideband FM or a narrowband FM. Therefore, it becomes necessary to look at its spectral content. So we'll connect this waveform, this signal to the spectrum analyzer and look at its spectral content. Now, the beta value was given by delta f by b, and delta f in turn was proportional to np, the amplitude of the message signal. If I change the amplitude of message signal, I will be changing beta, and therefore I will be going from wideband FM to narrowband FM. Let us now reduce the amplitude of message signal and see what happens. Now I have made the amplitude of message signal 0. That means I must have only one peak, which is the peak of the carrier. Okay, so in this case, let's move the marker. So let's say about 498 kilohertz. We measured it as 500, but it's possible that the voltage control oscillator is not stable. The frequency may be slowly drifting with time. So what we measured in the beginning as 500 kilohertz is 498 kilohertz. There is a small change in the frequency. Now this is our carrier frequency when I am not impressing any information on the carrier. Now let me slowly increase the amplitude of the message signal and let us see what happens. Now in this situation, notice that in addition to the carrier peak, I have one sideband here, one sideband here. There is also a small sideband here, a small sideband here. If I reduce the message signal amplitude a little bit, then these two sidebands should disappear. They are almost not there. So in this situation, this is similar to amplitude modulation. This is the case of a narrowband FM. This is the case of a narrowband FM, similar to having upper sideband, lower sideband and the carrier. This happens when the beta value is very small. Now supposing I begin to increase the amplitude of the message signal. Watch what happens. As I increase the amplitude of message signal, what is happening is, look at the number of sidebands. They have increased. The sidebands have increased because when I increase the amplitude of the message signal, I am increasing delta f. If I increase delta f, I am increasing beta. I am going from smaller values of beta to larger values of beta. Then the beta. Now let us look at the positions of the sideband. The carrier frequency is 498 kilohertz. Remember, we measured the message signal frequency to be 20 kilohertz. So the first sideband, upper sideband, will lie at 498 plus 20 kilohertz. That's about 518 kilohertz. Okay. The second peak would come at another 20 kilohertz separation. So this will be 538 kilohertz. That's about 538 kilohertz. The third one would be 558 kilohertz. So it's FC plus FM, FC plus 2FM, FC plus 3FM, and so on. Likewise on this side, you will have FC minus FM, FC minus 2FM, FC minus 3FM, and so on. If I increase the message signal amplitude further, you will have more sidebands. You will have FC plus 4FM, FC minus 4FM, FC plus 5FM, FC minus 5FM. Though a frequency modulated signal is supposed to have infinite bandwidth, there is an effective bandwidth given by Carson's formula. So Carson's formula enables you to calculate the bandwidth of a frequency modulated signal. If you want to make sure that this FM signal is transmitted over a channel with minimal distortion, you must make sure that the bandwidth of the signal falls well within the bandwidth of the channel over which you are trying to propagate it. Now, frequency modulation together with phase modulation. Phase modulation is another kind of modulation scheme. Frequency modulation together with phase modulation are called as angle modulation schemes. Angle modulation scheme together with amplitude modulation is in general called as analog modulation scheme. In the next demonstration, we will see how we can demodulate frequency modulated signals. We have seen how we demodulate amplitude modulation signals. We will see how to demodulate frequency modulated signals.